Gradients of curves. The gradient of a curve is constantly changing. It's not the same as it is with a straight line. Now we can find the gradient of a curve at a particular point by considering the tangent at that point. The tangent obviously just touches the curve at that point, and that line, its gradient, represents the gradient of the curve at that particular point. Now, finding the derivative is what we're going to look at first of all here, finding this gradient function. Now, if you look at this illustration here, this diagram, we can see that we've got lines joining A to B. Now, we are trying to determine the gradient at the point A. Now, as those points A and B get closer and closer together, so as the point B comes closer and closer together, the blue line becomes closer and closer to the true tangent, which is the red line shown at A. So if we look at this in a bit more zoomed in version of that graph, which is what we have here, that point B, we want to get that as close to A as possible. So what we say is we can say that let the x value of the point A be x0, and let the x value of the point B be x0 plus h, where h is a very small change. And that h being so small means that A and B are very close together, and so then we are getting closer to the true tangent. The true tangent will be when h approaches 0, in the limit as h approaches 0, which is what we'll look at. So to find this gradient, we will be looking at the difference in y, which is this difference here, divided by the difference in x, as we do to find the gradient of a straight line. But this time, obviously, we're going to be using the function y equals f of x, whatever that may be, to find that gradient. So the gradient of a curve is found by looking at the difference in y between those 2 points A and B, which then simplifies essentially to this. So the y value at B becomes, well, whatever we substitute the input, when we substitute the input x0 plus h into f of x, which is this bit, minus when we substitute x0 into f of x at A, which is this. So this is the difference in y, divided by the difference in x, which is x0 plus h minus x0, which is this bit here. So the gradient of AB is represented by this. And in the limit, as that point, or as that value of h becomes closer and closer, as it tends towards 0, then we can use this to find the exact gradient of the function at that particular point. So here is our equation to find the gradient, which is given to us in the formula book. This is how we find the gradient from first principles. So let's take a look at applying this to a particular example. So this would be used whenever the question asks us to find the gradient or the derivative or differentiate from first principles. So here we have a function given to us, and we want to find out what its derivative is, or we want to show that the derivative of x cubed is going to be 3x squared. So let f of x equal to x cubed. Now x cubed is obviously a curve, it's a cubic, but let's just take a look at a particular point here. We're going to apply our function here. So we're going to say that f dashed of x, which is the gradient function, is equal to f of x plus h. So we've got f of x plus h minus f of x all over h. So what is f of x plus h? Well, let's just make a note of what f of x plus h is on the side. So f of x plus h is equal to x plus h all cubed. So then we have, what is that? Let's take a look at that. Let's actually expand that. So we've got x plus h all cubed minus f of x, which is x cubed all over h. Expanding and tidying this up, we have x plus h, x plus h, x plus h minus x cubed all over h. Expanding the first two brackets gets us x squared plus 2x h plus h squared multiplied by x plus h minus x cubed all over h. Tidying this up further, multiplying this big bracket by the second bracket x plus h gives us x cubed plus x squared h plus 2x squared h plus 2x h squared plus h squared x plus h cubed minus the x cubed at the end all over h. X cubed minus x cubed is nothing. Then we have x squared h plus 2x squared h. So we can collect like terms here. These two terms are like terms here. So that gives us 3 lots of x squared h. And then we have 2x h squared plus 1x h squared, which are also like terms. And adding those together gives us 3x h squared plus h cubed all over h. If we then divide all the terms through by h, we get 3x squared plus 3x h plus h squared. Now remember, the true gradient is when h tends towards 0, in the limit as h tends towards 0. So then we look at what is f dashed x. In the limit as h tends towards 0, it becomes 3x squared plus 3xh. This term becomes a 0 because the h tends towards 0 plus h squared, and as the h approaches 0, that term also becomes 0. So then in the limit as h tends towards 0, as h becomes very small, the actual gradient function is equal to simply 3x squared. So there we have shown that the differentiation or the derivative of x cubed is 3x squared as required.